So we'll now discuss a category of IRs or intermediate representations called static single assignment IRs or SSAs. So to understand what is SSA IR, consider the following code: x equals y plus z, x equals x plus 1, w equals y plus z, and v equals x plus 3. Now let's focus on the variable x. And x is being assigned twice here. And the first assignment is for value y plus z, and the second assignment is for value x plus 1. And interestingly, later on, y plus z is a value that is recomputed, but this time stored in w. Now the problem here is that I could have reused the computation of y plus z, but only the problem is it has already been overwritten, right? So for example, this particular computation can be reused here, right? However, the problem is that this computation was available in the variable x, but x has now been clobbered with some other value, and so it's no longer reusable. So how do you solve this problem? And one answer to this problem is the SSA form. So what is the SSA form? Well, it just creates different versions of every variable such that every version has only one assignment to it. So for example, for x, we have two versions, x1 and x2. And for w and v, because that they are being only assigned once in this program, we just have w1 and v1. And when we do this, then we also change the uses of x. So for example, x1, depending on what version is reaching where. So at this point of x, this version is reaching, so we just label it x1. This is x2, and so everything below x2's assignment will basically get renamed to x2. Every use of x below x, this assignment is going to get used to x2, and so this particular assignment, this particular use of x gets renamed to x2. So this is called static single assignment because it's a single assignment for every variable in a static. When you're looking at the static program, it doesn't mean that dynamically every variable is going to get assigned only once, because if there's a loop, for example, then the same static variable can get assigned twice, right? So the same version variable, for example, if there was a loop like this, then x1 can get assigned multiple times, but in the static context, it's only being assigned once. And using the static single assignment, we can create this optimization now, and we can say w1 equals x1. All right, instead of x1 equals y plus z, and that's an optimization because we have saved the computation, recomputation of y plus z. So why do we care about SSA? We have already seen one example where there is some optimization enabled because of using SSA. But basically, we're going to see that optimization algorithms become simpler if each variable has only one definition, because then we don't have to track the location or the different versions of every variable. Because every variable has only one definition, every variable has only one version, and so it's easy to talk about variables from there on and not worry about the variable value at a particular location or anything like that. Also, unrelated uses of the same variable become independent. So for example, we saw the use of x1 equals y plus z and x2 equals x1 plus 1. Now x2 and x1 are now completely independent variables, and they can be used independent of each other. For example, it is possible that x1's computation can get reused, or similar thing could have happened for x2. And the third very important reason to use SSA is that more values become available at each program point. So even for the example that we just saw, when we do w equals y plus z, now there are two values available there. There's x1 and x2, which are both available, and one of them, those values actually happens to be the same value that we want to compute into w at that program point. And so because both the x1 and x2 are available, that helps, and we can just say w equals x1. Right? On the other hand, if I didn't have SSA, only one of x1 or x2 would have been available at that particular program point, and maybe I would have missed the optimization because of that. So these are some important advantages of SSA, and that's why SSA is a very popular method to do IR design, and because many optimizations become easier on SSA IR. In fact, LLVM IR is also an SSA IR. Okay, So how do you convert to SSA? So, when we did our code generation, we basically didn't have SSA. So we recall the igen function that would take abstract syntax tree and generate the IR code for that. And in that, we didn't really discuss how to generate, an SSA IR. We're just generating a regular IR where it is possible for the same variable to be assigned more than once. But if I have such an IR, then it's possible to convert it into an SSA form. So any program that is not originally in SSA form can be converted into an SSA form, and the idea is very simple. We're going to replace the target of each assignment with a new variable. So for example, x becomes x1, and if x is assigned again, then that becomes x2, and so on and so forth. And then we're going to replace each use of a variable with the version of the variable reaching that point. And this is exactly what we did in the example that we just saw. So for every use of that variable, you're going to see what is the version that is reaching here. And depending on the version that is reaching there, we are going to rename it with the appropriate version name of that particular variable. So let's again look at this example. We have this this IR, which is not in SSA form, because you can see that x is being assigned twice in this particular program. And then what I'm going to do is I'm going to say, okay, for every assignment, I'm going to rename it to new variable. So I basically say x becomes x1, and the first assignment becomes x1, and the second assignment becomes x2. Similarly, the first use, the use of x in a is equal to b plus x is basically being reached by the definition x1, and so here it becomes x1. And similarly, in this particular statement, y equals x minus a, the use of x that is being used is x2, and so this becomes x2 minus a. All right, so but that was just for a single straight line sequence of code. Here is a slightly more complicated example which has some control flow in it. So let's say the first instruction is x equals y plus z. Let's say the second instruction is x equals x plus 2. And then maybe I want to check whether x is less than 42 or not. If it is, then I want to go to this branch and say y equals a plus b and x equals 3. If not, then I say y equals 0. And here they both meet, these both paths meet. And then here I want to say z equals x plus y. Now I want to know, there are two variables here that are of interest, x and y. There's also z, but z is kind of only being assigned once. X is being assigned thrice actually, 1, 2 and 3, and y is being assigned twice, 1 and 2. All right, and the question is how am I going to rename this? So for example, it could be easy. I could just say this is x1, this is x2. I could say this is y1, this is y2, and now I need to rename, right? So this, what is the version of x that's reaching this point? It's x2, so I'm going to say 2 here. And then what is the version of x that's reaching here? Well, it's again x2, so I'm going to say 2 here as well. And then the question is, what is the version of x that is reaching here? And the answer is again 2, because on both paths it is actually the same version x2 that is reaching here. All right, so I'm going to say 2. Now I want to do the same thing for y. So y, y1 and y2. And what are the uses of y? Y is being used only at this particular location when we are assigning to z. But now we have a problem, because on one path it's y1 that's reaching, and on another path it's y2 that's reaching. So which one should I use? Actually, it will be incorrect to use any one of them, and so we need to do something about this. All right, and so before we are able to answer this question, let me just first pose this question. So question is, what should be the version for y here? Okay, and that's a problem in this SSA representation, and we're going to see what is the solution for this problem. But before we look at that, let's first use some definitions. So I'm going to define the notion of a basic block. What is a basic block? A basic block is a maximal sequence of instructions with no labels except at the first instruction. When I say no labels, which basically means that the internal instructions should have no labels, which means nobody should be able to jump to the middle of a basic block. Somebody can jump to the first instruction of the basic block, but never to the middle of the basic block. Here I'm assuming that you can only, the program can only jump to labels, and that's what no labels is supposed to signify, and no jumps except in the last instruction. So there should not be any outbound control flow from the basic block except at the last instruction. All right. So let's look at this. This whole, in fact, the way I've drawn this, all these rectangles here represent basic blocks. Okay. And actually I will show that no kind of bigger rectangles can be created here, because if I try to create bigger rectangles, I'll have one of the conditions being violated. For example, if I try to include y equals a plus b into the first basic block, then the second condition gets violated because the middle instruction is jumping out. And similarly, if I try to include let's say z equals x plus y into this one, then I have the first condition that's being violated, because now I'll have a jump to the middle of that particular basic block. And so this is the right basic block decomposition of this particular program. So what's the basic idea? The basic idea is that it should not be possible to jump into the middle of a basic block except at the beginning. You shouldn't be able to jump out of a basic block from in the middle. You're allowed to jump at the end, but not from the middle. And basically, it should be a single entry, single exit, straight line code segment. All right. So this is an easy way to remember: single entry, single exit, straight line. All right. So these are the three adjectives. So any code segment which kind of satisfies these three adjectives is a basic block. So with that definition, let's try to understand what are the versions that are reaching for y. So for x, we know it's x2, but for y, what are the versions that are reaching here? And we want to say that if I'm on this path, then it's 1, and if I'm on this path, then it's 2. Okay. And so how do I represent that? The solution is we have the notion of a phi node, or also known as the phi function. All right. And you basically define a new version of y3, and you say y3 equals phi 1 comma y2. All right, which means that y3 can be either y1 or y2 depending on whether it came from this path or from the second path. So these arguments are actually an ordered set, right? The order also represents the order of control flow edges. So we are also assuming that the incoming control flow edges are ordered. So this is the first edge. So let me just write it. Let's say this is the first edge and this is the second edge. And so if I'm coming from the first edge, then y3 is y1. And if I'm coming from the second edge, then y3 is y2. And now I can say z equals x2 plus y3. All right. So I'm using a special function or node called phi function or phi node. And I'm defining the semantics so that it chooses appropriately depending on which incoming edge the value came from, and then that's what gets assigned to a new version of the variable y3 in this case, and that's the version that we get to use in all uses of y from there on, because that's the version that reaches all the uses of y from there on. Okay, so phi function chooses the version depending on the incoming edge. All right, that's important. It's not a non-deterministic thing. It's a completely deterministic value returned, which is based on what is the incoming edge that was traversed to reach that particular basic block. And one of the very important properties is that it is only present at the beginning of a basic block. All right, so phi function is only present at the beginning of the basic block because that is the only place where there can be potentially multiple incoming edges. And so the phi function problem can only happen when you have multiple incoming edges and there are different versions that are flowing on those two different incoming edges. And so the phi function will basically help resolve that problem by letting you choose the version depending on which incoming edge was traversed.